Hello everyone, we are continuing class 12 chemistry, chapter 9, coordination compounds. We are doing crystal field theory. This is part 3 of that topic. Here we will be discussing spectrochemical series and then we will proceed to understand how the electrons in the d orbital of the central metal atom of coordination complexes get rearranged when it is approached by ligands. Please watch the video completely so that you get everything connected with crystal field theory clear. Do not forget to subscribe and support my channel. I am Anandavalli. Welcome to Guidance Education channel. Spectrochemical series is the arrangement of ligands in the increasing order of their crystal field splitting energy, which is also known as crystal field stabilizing energy, CFSE. We have already seen that for octahedral complexes it is represented as delta O, O for octahedral. The 5 degenerate orientations of the d orbital split up into high energy Eg and low energy T2G sets. The energy barrier between these two sets is what we call delta O in the case of octahedral complexes. Remember, this splitting is caused or initiated by the approaching ligand. The strength of the electric field of the ligand will decide the crystal field stabilizing energy. A few ligands of the spectrochemical series are given here. Please go through that. There are negative ions as well as neutral molecules. Since the ligands are arranged in the increasing order of their electric field or crystal field splitting or stabilizing energy, those ions on the left hand side have less stabilizing energy and those on the right hand side have greater stabilizing energy. From the list you understand that iodide ion has the least stabilizing energy and carbon monoxide, which is a neutral molecule, has greatest stabilizing energy. The crystal field splitting energy or crystal field stabilizing energy for these ligands have been experimentally determined, especially for octahedral compounds. And on the left hand side, the ligands are weak field ligands and on the right hand side, they are strong field ligands. Now we will proceed to understand how the electrons in the d orbitals get rearranged when strong field ligands and weak field ligands approach this central metal atom. This is how the d orbitals of the central metal atom get split up from the ground state when approached by a ligand. You are already familiar with this diagram. When the ligands approach the central metal atom along the axial line, the two axial orbitals gain more energy and they are called Eg orbitals. And the remaining 3 get lower energy and they are the T2G orbital. Energy of the T2G orbitals is lower than Eg orbitals, but it is definitely higher than the energy possessed by these orbitals in the ground state. In the excited condition, the average energy of the 5 d orbitals is taken as 0, that is the barycenter, and the Eg orbitals gain energy about 0.6 more than that of the average energy, noted as 3/5 of the average energy. And the T2G orbitals have 0.4 less energy than the average, written as 2/5 of the average energy. This value is given in negative sign and the other one is given a positive sign. For further discussion, we will show these two Eg orbitals as 2 boxes at a higher level and the T2G orbitals as 3 boxes at a lower level. The maximum number of electrons the 5 orientations of the d orbital can accommodate is 10. In the free state, all the 5 orbitals are degenerate. They have the same energy. So the electrons can go into any orbital. But when it is approached by a ligand, the degeneracy is lost. So the filling up of electrons change. We will proceed to see what happens in the case of weak ligands as well as strong ligands. In the octahedral coordination complex, there is a central metal atom and 6 ligands attached to it. But here we are talking only about the 5 d orbitals which form 5 bonds. Please remember this point. So the bond formed by one of the ligands is not considered here. So the central metal atom has to be really considered as an ion. Now we will see the different possibilities of the 10 electrons entering the 5 orbitals when approached by ligands. In the periodic table, the transition elements, that is the d block elements, come under groups from 3 to 12. The general electron configuration for d block is n-1 d 1 to 10, where n is the number of the period. As we move from group 3 to 12, these 1 to 10 electrons go on increasing. That is, in group 3, there will be 1 electron in the outermost d subshell. And in group 12, there will be 10 electrons in the outermost d shell. That is, all the 5 d subshells get filled up. In the free state, these electrons may occupy any orientation of the d subshell. But as the ligand approaches, this degeneracy of the 5 orientations of the d subshell is lost. We will see the details. For convenience of discussion, we will consider the ions of these various d block elements as d1 ion, d2 ion, d3 ion, etc. up to d10 ions. For d1, d2 and d3 ions, the number of electrons vary from 1 to 3 in the d subshell. We have already seen that as a result of crystal field splitting, 3 d orbitals have less energy called T2g and 2 Eg orbitals at higher energy level. So electrons have first to go to the lower energy orbitals. Then only it can fill the higher energy level, namely Eg. Therefore, for d1, d2 and d3 metal ions, there is only one option of electron distribution. From d4 to d7 metal ions, there are 2 possible options. Come, let us see that. The d4 metal ion has 4 electrons. In the outermost shell, 3 electrons first fill the T2g orbitals. The 4th electron has 2 options. One option is it may pair up with 1 electron in the T2g orbital. The Eg orbitals are totally free, empty. One of the T2g orbital has paired electrons. The other option is the 4th electron may enter one of the orbitals of the Eg, that is higher energy level. There are no paired electrons. In the case of d5 metal ion, there are 5 electrons in the outermost d subshell. 2 of the T2g orbital have paired electrons and both the Eg orbitals are free. There is one unpaired electron. The other possible arrangement is that 3 electrons enter the T2g orbitals and 2 electrons enter the Eg orbital. So there is no pairing of electrons. All the orbitals have unpaired electrons. Now coming to d6 metal ion, it has 6 electrons in its outermost d orbital. Under option 1, all the 3 T2g orbitals have paired electrons. All the 6 electrons are consumed there and the Eg orbitals are totally free. No unpaired electrons. Under the second option, one of the T2G orbitals only has paired electrons, all the others have unpaired electrons. For D7 metal ions, there are 7 electrons in the outermost d orbital, and all the 3 T2G orbitals have paired electrons, and one of the orbitals in the EG orbital has a single unpaired electron. One EG orbital is free. The other possibility is 2 of the T2G orbitals have paired electrons and the rest of the orbitals have unpaired single electrons. In either of the options, we find that pairing first occurs in the T2G orbital because it is at a lower energy level. And lastly, for D8, D9 and D10 metal ions, there can be only one option because all the T2G orbitals have paired electrons and the EG orbitals have either paired electrons or unpaired electrons. Coming back to D4, D5, D6 and D7 metal ions, the two different possibilities is because of the type of the ligand approaching the metal ion. The first type of arrangement gives rise to low spin complexes when it binds with the ligands. In this type, you can notice that the T2G orbitals have paired electrons. Pairing takes place there. The metal ions having the second type of electron arrangement forms high spin complexes. Please note that in this case, the orbitals have unpaired electrons excepting D6 and D7 where 1 or 2 orbitals have paired electrons. Ligands with strong crystal field stabilizing energy form low spin complexes and those ligands with low crystal field stabilizing energy form high spin complexes. Please also note the crystal field stabilizing energy for high spin and low spin octahedral complexes. I have given it there. Pairing of electrons is decided by a quantity called pairing energy represented by the letter P. Because for pairing, there should be enough energy to overcome the repulsion by the other electron. In the case of octahedral complexes, if the crystal field stabilizing energy is less than pairing energy, then there won't be pairing. The fourth electron will move to the EG orbital, resulting in high spin complexes. Whereas, if the crystal field stabilizing energy is greater than pairing energy, then pairing occurs and low spin complexes result. I have explained each and every point in detail so that it becomes easy when we start discussing certain properties like color of coordination compounds. That we will discuss in the next video. The video is already very long. Thank you very much.